Welcome. In this video we are looking at section 3.2, looking at Hubble's law, which explains the expansion of the universe and ultimately the theory of the Big Bang. So how did Hubble come up with this idea of an expanding universe? Well, it's all to do with light. When we look at the light from the sun, we've already covered this, there are certain absorption lines in the spectrum of light from the sun which are to do with the Balmer series, the fact that hydrogen, which we know to be the most abundant element in the universe, is absorbing certain frequencies, certain wavelengths of light out of the spectrum. When we compare this to light from distant galaxies, we find, or this is what Hubble looked at, he noticed that the bands had been moved. Okay, and as you can see that these lines have been moved towards the red end of the spectrum. Now what that means, what Hubble realized, was that if those lines have been moved towards the red end, then from what we've looked at before, from the idea of Doppler, that means that those galaxies are moving away from us. Okay, so he looked at these galaxies, he said, well, I'm looking up at all these distant galaxies and stars, and I'm looking to see if there are any that are going to come towards us, and first of all, there's none, or there's hardly any. And he found that when he looked up in the sky, he started looking at the relationship between how far away they were and how fast they were moving away from us. And what he realized was that the further away an object is, a distant galaxy is, the faster it seems to be moving away. Okay, so you can see on this graph here, on the x-axis we have the apparent distance, or the distance in megaparsecs. This is how far away these galaxies are in megaparsecs. And then from calculating the redshift, from looking at the redshift of these different galaxies, and then using Doppler to work out the actual speed at which they are moving away from us, the speed at which they are receding from us, that's the recessional velocity, Hubble was able to work out the Hubble constant, the Hubble law. And the Hubble law basically says that the further away something is, the faster it's moving away from us. Okay? And the Hubble constant h is the ratio of the recessional velocity to the distance from the Earth. Now the units for it are not very standard. They are the recessional velocity in kilometers per second per megaparsec. And you can see here that from this graph, you can see there's a solid band that runs through the middle of the line of best fit, runs along basically 65 kilometers per second per megaparsec. That is the Hubble constant, 65 kilometers per second per megaparsec. So what that means, if something is 1 megaparsec away from us, then it would be moving away from us at a recessional speed of 65 kilometers per second. If it was 100 megaparsecs away from us, then it would be moving away at 6,500 kilometers per second, and so on. Okay, so that is the Hubble constant, and that's what Hubble's law says. It says the further away you are, the faster you're moving. Now notice that there is quite a large deviation between the highest value it could be and the lowest value it could be, and that is because there's, as you're looking at further and further galaxies, there is greater error in the measurement of the distance. Okay, and that is because of the uncertainties in the apparent magnitude that we can detect from Earth. Obviously we have a measurement of the apparent magnitude, and there was a degree of uncertainty in that, and the greater the distance to a distant galaxy, the larger the percentage error becomes. And so you can see as we go further out, the error bars for the light spectrum from these supernovae, which are the standard candles which we use to look for distant galaxies, as we look further out, those error bars become greater. Okay, so you may well be asked as an exam question to take a graph like this, draw a line of best fit, and work out a value for the Hubble constant, and you would give that value in velocity in kilometers per second per megaparsec, and you're looking for a value that should come out somewhere around about 65 kilometers per second per megaparsec mark. Okay, so that's Hubble's law. Now, basically, what this tells us is the universe is expanding. It means that it's also jumping out into all directions. Okay, he showed that the further away galaxies are, the more redshift they have, and so the further apart they are, the faster they're moving. This basically tells us that the universe is expanding, and this as a result of this, of course, if the universe is expanding, that started the whole idea of the fact that that the universe must be coming from a point, and so this led, if we go backwards in time, this led to the concept of the Big Bang. Okay, now it's really important to understand about the Big Bang. One of the things that most students really struggle to get their head around is the fact that space was created at the point of the Big Bang. So it's very easy to visualize space, and you're standing a little way away looking at the point where the Big Bang happens, and you visualize an explosion in space, and this Big Bang moves out, and all the matter in the universe moves out through space. But that's not really what's happening. At the point of the Big Bang, space itself was created. Before the Big Bang, it's very hard to imagine, but before the Big Bang there really wasn't any space, there really wasn't any matter, there really wasn't any time. Okay, so at the point of the Big Bang, all the matter in the universe comes into existence, and the space in the universe comes into existence. And so, to explain this idea of redshift, at the beginning of the universe, when matter and space was being created, light was being created from these galaxies as they are formed, and it would have had a given wavelength. And over time, the whole universe has expanded, space itself has expanded, and as a result, the wavelength of light that is moving through space has expanded with it. And so this is the first sort of reason to try to get your head around the idea that we can sit on Earth and look out at the Big Bang, look out in space and look in every direction from Earth and see galaxies in all directions around us and still find they're all moving away from us. We may as well be at the centre of the universe. Any point in the universe may as well be at the centre of the universe, because it's space itself that is expanding, as opposed to the universe expanding through pre-existing space. So Hubble's law is not without its limitations, and in simply speaking, the big problem with Hubble's law is the fact that there's not that much light that gets to us from these very distant galaxies. Therefore, any small uncertainty we have in measuring the amount of light or the apparent magnitude creates an ongoing uncertainty in the distance to it. And so, therefore, Hubble's law is good, but it's not perfect. Now, what it has done and what it's allowed us to do, as we've said, is it's allowed us to understand this principle of the Big Bang. And of course, it's to summarise the Big Bang. It basically, if we work everything back, we can say, well, space and time and matter, and it all began at this point. We call it the Big Bang. Before the Big Bang, this is the thing that most people struggle with, there was no space. Okay, no matter, and no matter is fine. But most people struggle with the idea of there being no time and no space before the Big Bang. But that you really must try and get your head around that to the best of your ability by watching more YouTube videos, I guess. And of course, space has been constantly being created since the Big Bang, and of course, space is continuing to be created as a result of the Big Bang. Now, let's work this back. If space is being created and also time is being created, we can start to use this principle to work out, we can use Hubble's law to work out the age of the universe. So, if you think about a galaxy moving at a constant velocity, then we can say, well, we know the speed equation, speed is distance over time, and time is distance over speed or velocity. Hubble's law tells us that the Hubble constant h is the ratio of the velocity to the distance. So we can put these two equations together and we can say, well, time should be distance over the Hubble constant times the distance, and therefore the distances cancel out and we get 1 over h. And so using this idea, 1 over the Hubble constant should give us a rough approximation for the age of the universe. Now, it's worth mentioning at this time, we've just said the Hubble constant is 65 kilometers per second per milliparsec. So if you divide 1 by 65, you will get 0.1. Now obviously the universe is a little bit more than 0.1 seconds old, so we need to convert the distance on the bottom, the Hubble constant, the distance in megaparsecs to meters, and of course the kilometers per second to meters, to give us h in seconds to the -1. So on the next slide we'll have a look at that. So if we're going to try to work out the age of the universe from the Hubble constant, and remember we can say that we think that time is going to be the inverse 1 over the Hubble constant, then we need to really convert this value here from kilometers per megaparsec to seconds to the -1 to work this out. So let's have a look at how we can do this. We've understood at the moment that the Hubble constant h is 65 kilometers per second per megaparsec. So this of course is distance, this of course is distance, so it should all cancel out to just give us h should just have the units of seconds to the -1, but of course we've got to convert these units to make them the same, got to just get them to meters. So here's how we're going to do this. We're going to basically say that the Hubble constant is 65,000, because it's kilometers, divided by however long a megaparsec is. Let's start at the start. Well, it's mega, so it's 10 to the 6. A parsec is 3.26 light years. 3.26 light years, and of course 3.26 light years is the distance light travels in 1 year. So the speed of light is 3 times 10 to the 8. And the distance, the time that it's going to travel in 1 year is going to be a year in seconds, which is 365 times by 24 hours in a day times by 3,600 seconds in an hour. Now when you do all this, this value will come out to round about 2.11 times 10 to the -18 seconds to the -1. And if so, we can now that we've got the Hubble constant into, it's just in seconds to the -1, we can work out the age of the universe by doing 1 over this, and this gives us somewhere in the region, if we use 65 kilometers per second per megaparsec, it comes out to 4.74 times 10 to the 17 seconds. Now if we convert that into years, then that comes out to round about 1.5 times 10 to the 10, which is 15 billion, which is greater than the accepted value for the age of the universe. The age of the universe is actually about 13 billion years. So there is obviously this we'll come to this in a bit, but this basically it's not the greatest way of working out the age of the universe, but it gets you in the right ballpark. Okay, if we use a value of 75, you'll come out with a value closer to the accepted age of the universe, and we'll come to why this is the case in a minute. So if you want to pause the video, you might want to just practice that bit of maths, because it's required. Assuming you've done this now, then you should come out with those two values there, 10 to the 17 seconds and more like 13 billion years, which is the accepted value. Now the reason this is an estimation or an uncertainty is because we're assuming at this stage there's a constant expansion, a constant rate of expansion. That's the first thing, and the second thing is that the reason this is an estimate is because Hubble's constant has a large uncertainty. But what we're going to come to now is the fact that really the universe is not expanding at a constant rate. So we've seen evidence for the Big Bang in terms of redshift. The next piece of evidence that suggests that, or confirms the Big Bang, is the ratio of hydrogen to helium. Now, theoretical physics beyond the scope of the specification predicts a 7-to-1 ratio of protons to neutrons because of their rest masses and how quickly they basically cool at the start of the universe. The mass we see of the universe is I mean, everything else apart from hydrogen and helium is negligible in the universe as it stands, and it's 75% hydrogen and 25% helium. So obviously, if we think of it in terms of a 12-to-1 ratio of hydrogen atoms to helium atoms, that gives us an observed mass of 75 to 25%. And yeah, 12 hydrogen atoms is obviously 12 protons. One helium atom is 2 protons and 2 neutrons, so that's altogether 14 protons to 2 neutrons, and that does indeed mean that there is a 7-to-1 ratio. And this is, you know, the reasonings behind the 7-to-1 ratio is beyond the scope of the specification, but the ratio of hydrogen to helium is a piece of evidence that suggests or corroborates the Big Bang model. Next up, the third piece of information that supports the Big Bang is the cosmic microwave background radiation. And essentially, the idea with this is that at the point of the Big Bang, there were a lot of high energy radiation being produced. And over time, as the universe has expanded, that high frequency, short wavelength radiation should have now expanded to the microwave level. And indeed, when you look up in the sky, there is pretty much in every direction a very even spread of this cosmic microwave background radiation, which is coming from all angles. And so as a result, basically we can say that the cosmic microwave radiation is just the third piece of evidence. We've got redshift, we've got the relative abundance of hydrogen to helium, and we've got cosmic microwave background radiation. So far we've got this idea that Hubble's law can tell us the universe is expanding. We can say the rate of expansion is greater the further away we look, and it leads us to this idea of the Big Bang. But of course, like all good theories, it has its bugs and its glitches, and we need to sort of address these now. So just to summarise really how we've come to this condition and how this assumption that the universe is expanding. We've looked at type 1a supernovae. As we know, they explode, they produce a measurable, or a predictable constant peak luminosity of minus 19.3, apparent magnitude of minus 19.3, sorry, an absolute magnitude of minus 19.3, and they show these absorption lines in the silicon range of the spectrum, and they're quite predictable, so we can spot where they are in space. We know, because we know their brightness, we can use them as standard candles. We know what their apparent magnitude. If we can measure their apparent magnitude, then we can obviously use the equation to work out how far apart they are. But there's two problems. There's not two problems. There's one problem. When we look at how bright they are and we measure the redshift from the absorption bands they show, the two do not agree. Okay, the redshift basically is smaller than the magnitude calculation, and that's basically saying that really they're further apart than the redshift says they should be. Okay, and this is really discovered very, very recently, and the only plausible explanation for this is that the universe is not actually expanding at a constant rate. Logic would dictate, if the Big Bang occurred and all the matter in the universe was shot out in all directions as space expanded, it would expand. But of course, gravity should keep pulling on these various planets in the galaxy, galaxies in the galaxy, and slow down the rate of expansion as time goes on. And so if you look at this graph here, this would be the Big Bang, this would be the explosion. We sort of would expect that this would curve this way as the expansion slowed down. And when we look back in time, and we will come to how we look further and further back in time, and this is from quasars, we'll look at that in a minute, but we, instead of finding this slowing expansion, what we find is it sort of slowed down for a bit, and then as time went on, it started to expand. And so we found that there's some mysterious force which is pushing galaxies apart and increasing the rate at which the universe itself expands. Now, we don't really know what it is. We've come up with the term for it, dark energy. Okay, and because of this, we've been able to work out how much of the universe is this mysterious force, this mysterious power, which we call dark energy. Now, nobody really knows what it is. All we know is that the universe is expanding far too fast to be doing on its own. So there's we don't know what it is, but we come up with this term dark energy to explain the fact that the universe is expanding faster than it should be. And it's bizarre, but when you actually consider, of course, we know now that energy and mass can be converted between the two. There's some sort of dark matter out there, which is responsible for galaxies swirling in ways that we don't expect them to. If you look at a galaxy, if there's a black hole in the middle, you would expect the stars nearest the centre of the galaxy to go around faster than the stars further away from the black hole in the middle, because of centripetal forces. But when we look at them, we find that actually the stars are going around in the galaxy, they're all going around at the same speed. So there must be some sort of dark matter, some matter that's applying some gravitational force that we can't see at all. That explains that. And there's got to be this dark energy that is pushing galaxies apart faster than we expect them to. And this is the extent of what we don't know. The bottom line is, at the moment, we estimate that the universe contains 73% dark energy, 23% dark matter, and only 4% matter. So the only stuff that we can really look at and observe and understand and explain is 4% of it. The rest of it is basically a mystery to science at the moment. There are various theories, but nothing's as yet been confirmed. So, where does this lead us? What's going to go on in the future? As we say at the moment, the universe is expanding at an increased rate. We don't really know whether it's going to continue to expand at an increased rate or slow down again at some other point, but there are three possible outcomes to this. The first one, of course, is a closed universe where something happens, it gets to a certain value, and then gravity causes it to collapse. Now, the closed universe model would suggest that there's going to be repeating incarnations of the same universe. It expands, creates, stops expanding, crushes down, and then explodes again. We have ongoing big bangs over billions of years cycles. The open universe basically tells us that the universe goes out, expands and expands on forever and ever and ever, and just keeps on basically expanding out forever and ever and ever. And the flat universe is the theory that it will come out and finally stop expanding and then just get to some value of sort of final size, and that's where it will be and stay there. But as yet, this is nobody really knows what's going to happen.